Hi guys, and welcome to our first video theory lesson, and we're going to start off this one with electric fields. Now this topic is found in chapter 10 of your textbook in part B if you're wanting to find any additional information. So the first thing we're going to have a look at is some work that was discovered in the late 19th century by a guy named Charles Coulomb, and we'll talk about him a fair bit. But some background information, basically if we have two charges, and remember that we covered charges when we looked at electrostatics, that there's a force between two charged bodies, and basically what we say is it's inversely proportional to the square of the distance between them. Now this sounds fancy, but in reality it's actually quite simple. It's saying that the force between two particles, if they are close together, the force will be big. If they are far apart, the force will be small, and that's just what it's saying down here. So if distance between them is big, it's going to be a small force. If the distance between them is small, it's going to be a large force, and that's what this inversely proportional wording actually means. So it does make pretty good sense. Now, basically, what it also says, or what we know, is the force between two charges is directly proportional to the strength of each charge. So if we say that Q1 and Q2 are our charges, and they represent the strength of the charge, then the force is going to be directly proportional to the size of the charge. So that means if we have a big charge, the force is going to be big. If the second charge is big, that force is also going to be big. So directly proportional means if one's big, the other is also big, or inversely, if it's small, then the other is going to be small. So the first thing we looked at was inversely proportional, which meant opposite, but directly proportional means the same. So big force, big charge, small force, small charge. Hopefully that makes sense. Now, if we put all of these together, we can say that the force is directly proportional, so same, to the product, multiply, of the two charges. So if we have Q1 times Q2, that's going to mean we've got our force. So if Q1 and Q2, or Q1 times Q2 is big, we're going to have a big force. If Q1 and Q times Q2 is small, we're going to have a small force. So basically the size of the charges reflects the size of the force that's going to happen between them. Now, if we combine these results, some of you might have seen this formula before, but what it's generally saying, oops, hang on, too far, is that the force between the two charges, so our force, is directly proportional to the square of the product of our size of the charges, and inversely proportional to the distance between them. So this is just putting together all the things we've thought of before, and we'll talk about K in a moment. Now, charge is measured in a unit called Coulomb, alright? So you remember before that I mentioned that Charles Coulomb was the one that discovered these mathematical relationships. He has the holy grail of science, as he now has a unit named after him. So typically, charged bodies are in the order of microcoulombs. So a fancy little U, microcoulombs, and that means that it's times 10 to the negative 6 coulombs. Alright, now an electron, we need to start remembering these ones because we'll use this quite a lot. An electron has the charge 1.6 times 10 to the neg 19. Now you'll find this on formula sheets if you need it, but it's a handy thing to start remembering. Now, a proton, as we know, is usually equal and opposite sign of an electron. That's how we keep atoms neutral. So an electron has a charge of 1.6 times 10 to the neg 19, and a proton is just equal but opposite. Alright, so the other one would have been minus 1.6, this one would be plus. So it takes 6.25 times 10 to the 18 electrons, so heaps, or protons, to create a charge of 1 coulomb. So that tells us that a coulomb is a pretty big charge. Now, here we go talking about that formula again. So it's called Coulomb's law. And as we said before, you can define it by saying the magnitude of the electrostatic force is directly proportional to the size of the charges and inversely proportional to the direction. Now, if we talk about breaking down this formula, we've got Q1 and Q2. They're the magnitudes of the charges, how big the charges are, or each of the charges we're looking at. R is our radius, or the distance between their centers. And remember that distance is always measured in newtons. And K, this guy here, is called the constant of proportionality. So basically, that's just a constant that makes it all work. And that constant is always the same. It's 9 times 10 to the 9 newtons per meter squared per coulomb to the -2. All right, and that's just basically a combination of all of these units to get the unit of K. We can talk about that more if you like. Now, to determine whether or not a force is attractive or repulsive, because Coulomb's law is only going to tell us the size of the force. Now, you remember that force is a vector, so vectors need to have a magnitude but also a direction. So it's really important that we know the direction of the force, so whether it's attractive or repulsive. And basically we can look at it like this. So any two stationary charges experience a mutual force, so equal and opposite, along the line joining the two centers. So the forces are attractive if the charges are of opposite sign, so one's positive and one's negative, and they're repulsive if they're both the same sign. So a negative and a negative will repel, a positive and a positive will repel, and opposite charges attract. So as usual, that saying opposites attract is very correct for charges. If we look at it in terms of a picture, it looks like this. So we've got a positive charge and a negative charge. There's going to be an attraction along the centers of their mass into the middle there. And if we have this one, we've got two like charges and they're going to repel. So in both cases, F1 or force 1 is equal and opposite to force 2. So Newton's third law, equal and opposite forces. Now, there is a dependence on the medium between the charges, and what that means is what type of material the charges are in. So whether or not they're in a vacuum, whether they're in air, whether or not they're suspended in a plastic or in oil, that kind of stuff. So this constant of proportionality can actually be replaced with this fancy looking equation here, which we can say as 1 over 4 pi epsilon naught. Now, what this little guy here is, epsilon naught, is called the coefficient of restitution, and that differs for each and every type of medium. Now, K is talking about, when we use this equation, it's talking about the medium between the two charges being a vacuum, and this one is more accurate because we can actually say whatever medium we're talking about. So to be more accurate, we actually use this one here. Now, the difference between a vacuum and in air is only, I think, 0.06%. So even when we're talking about our two charges in air, we can still use the same value for K. So if we look at that, epsilon naught, the permittivity of a vacuum is this here, and the medium between the two charges with oil or plastic, then epsilon naught will need to change. Now, if you're given that question in a test or in an exam, you will always be given epsilon naught if it's something obscure like plastic or oil, but generally it'll be in a vacuum or in air when we'll have the same K value each time, so it's nice and easy. Now, a coulomb is extremely large. If we consider two charges, each 1 coulomb separated by a distance of 1 meter in air. All right, we plug it into our equation here. We know that K is equal to 9 times 10 to the 9, 1 coulomb and 1 coulomb over 1 meter. We get this guy here, and it's saying that force is equal to 9 times 10 to the 9 newtons, which is actually the weight of a small car. So it's extremely huge. Now, I've got some examples to go through here. They shouldn't take too long, but if we're trying to calculate the force of repulsion between two small spheres that are each carrying a charge of 4 microcoulombs, and they are 0.5 meters apart in a vacuum, we've identified all the parts there, we have to find the force. So we use Coulomb's law. Force is equal to 1 over 4 pi epsilon naught times Q1, Q2 over R squared. over here, this all turns into 9 times 10 to the 9. So that goes on the top because it's only one number. It ends up being 9 times 10 to the 9 over 1, in which case we put it on the top. So you have to remember that. This value goes on the top. So 9 times 10 to the 9 times the charge, 10 times 10 to the neg 6 because it's microcoulombs for both of them. And our distance is 0.5 meters squared. So remember that we have to do r squared. If we work that out, we get our force here of 5.96 times 10 to the 1 newtons. Now, here we go. One of these are talking about, I'll just read it for you. But the magnitude of a force between two charges is 5 newtons. What is the magnitude of force if one charge is doubled in magnitude? The magnitude of one charge is multiplied by 3 and the other is multiplied by 1/4, and the distance between these charges doubles. Okay, how do we do that? Now, if one charge is doubled, Q1 is times by 2, then remember force must also be multiplied by 2 because they are proportional, they're directly proportional. If one gets bigger, the other gets bigger. So if one of them gets bigger by 2, the other one gets bigger by 2. So if it was originally 5 newtons, then now it's going to be 10 newtons. The next one, if the magnitude of one charge is multiplied by 3 and the other is multiplied by 1/4. So Q1 is multiplied by 3, then Q2 is multiplied by by 1/4. Then the same thing has to happen to the force. So first we multiply it by 3 and then we multiply it by 1/4. So first of all, you can do it all in one by going 3 divided by 4. You could do it in 2 steps. Either way, you have to times it by our original 5 Newton force, and we end up with a force of 3.75 newtons. Now, examiners love proportionality questions, and we're going to get a good handle on these to make sure that you guys are well prepared. The other one, if the distance between the charges doubled, so R is multiplied by 2, okay, so then F is multiplied by 1/2 squared. All right, so we put it down the bottom. All right, so it's going to be 1 over, because remember it was R was on the bottom, okay, so Q1, Q2 over R squared. So if 2 goes on the bottom, it ends up being 1 over 2. Or if it was 1/4, it'd be 1 over 4, and then all of that gets squared. So 1/2 squared, if you put that in your calculator, will give you 1/4. If you're not really good at fractions and need to put it in your calculator, that's absolutely fine. So we've got this number here, 1/4. So we know that the force is then times by 1/4. So 1/4 times our original force of 5 newtons will give us 1.25 newtons. Okay. Lastly, application. So Coulomb's law enables us to find the charge between two charges only, so Q1 and Q2. If we want to find the net force on, a charge, that's spelled incorrectly, sorry about that, due to the action of 2 or more charges, it gets a little bit more complicated. So we have to calculate the force due to each charge and then add them up vectorially. And I'll give you an example of how to do that in a minute. So the formula we need is to find the total charge, or the total force. It's the force on 1 plus the force on 2. So this is a little example. If you have 3 charged spheres, A, B, and C, and you wish to find the force on charge C due to the others, first you use Coulomb's law to find the charge on C due to the first one, and then you repeat this to find the force on C due to the other one, and then you add them vectorially to find the resultant, or the total force. Now, that sounds really complicated, and we'll actually do a bit of an example of it now, and my one piece of advice for you is to definitely use a diagram. So this is going to minimize the amount of mistakes that you make with adding up the force. All right, so stand by for a bit of an example. Okay, so let's have a look at an example. So first of all, we've got a question here that's talking about charges, and we've got 3 of them. So our normal Coulomb's law, we still have to apply, but it's going to be a lot harder. So 2 charges, Q1 and Q2, of magnitude 20 microcoulombs and 10 microcoulombs respectively, are placed 50 centimeters apart in a vacuum. So already they've identified the medium. A third charge, Q3, which is positive 30 microcoulombs, is placed midway between Q1 and Q2. And they're asking us to find the force on this guy here, all right, from the other two. And there's two scenarios. The first one is if Q1 and Q2 are both positive, and the second one is if Q1 is positive and Q2 is negative. So the first thing we need to do is write down all the information that the question actually gives us. So first of all, we know, whoops, hang on, wait a second, I've hit things. So Q1 is equal to 20 microcoulombs, which is equal to 2.0 times 10 to the neg 5 coulombs. Q2 is equal to 10 microcoulombs, which is equal to 1.0 times 10 to the neg 5 coulombs. And we have Q3, which is the guy in the middle. He's 30 microcoulombs, which is 3.0 times 10 to the neg 5. So when we're told in the question 20, 10 and 50, there's two significant figures, so that's why we've changed it to two significant figures in our scientific notation. The other thing we're told in the question is the radius. So the radius between them is 25 centimeters. All right, so 25 centimeters, and the radius is between the ones we're looking at. So remember, we have to talk about, we want to know the charge on Q3 from Q1. So the distance between Q1 and Q3 is only 25, and vice versa from the other one. So 25 centimeters, remember SI units for distance is meters. We're looking at 0.25 meters. All right, we know all that. The next thing we know is our formula. So we have to figure out the one of them first, but the charge on the middle one from Q1 and then the charge on the middle one from Q2, but both times we're going to use the same formula. 1 over 4 pi epsilon naught times by Q1 Q2 over R squared. So this is our Coulomb's law we talked about. So step 1, we're looking at Q1 on Q3. All right, so to do that, we want to know the force, number 1. We're looking at 9 times 10 to the 9. Remember, that's our 4 pi epsilon naught. Cancels out to just be 9 times 10 to the 9. And then we put in our charges. So Q1 is 2 times 10 to the neg 5. Q2 is Q3, because that's the one we're looking at here, is 3 times 10 to the neg 5. And we put that over our radius. It's good to keep it in brackets nice and neat, because it's getting squared. And if we do that, we're getting a total of force 1 is equal to 8.64 times 10 newtons. Now, if we change that, we can just change it to 86.4 newtons. So that's from Q1 on to Q3. But now we need to know what Q2 is exerting on Q3. So step 2 is Q3 on Q2. So we do the same thing again. We're looking for force number 2 now. So 9 times 10 to the 9 for 4 pi epsilon naught. And then our charges. Q3 is 1 times 10 to the neg 5 from our stuff up the top. And we're timesing that by Q3, which is 3 times 10 to the 5, minus 5. And again, the distance is the same. So 0.25 squared. Apologies for my messy writing. This pen is not super, but it's working okay. So that gives us 4.32 times 10 newtons, or 43.2 newtons for force number 2. Now we've got the magnitude of the force, and remember, for the direction we actually have to add them vectorially. So let's do that now. So if we're doing question number 1, and in that situation they were both positive, There we go. It means that F1 and F2 are in opposite directions. All right, so if we're standing at Q3, all right, so we're standing in the middle here at Q3, and 1 is over here, so force number, the first one, so Q1 is here, it's going to be positive, all right, and force number 2 over here, so Q2, if that one's in the middle, Q3, what happens is that they're going to be pushing in opposite directions. So if they're both positive, they're going to be repelling each other, aren't they? So what's going to happen is that this guy is going to be repelling, it's going to be pushing, so if we're standing here, this one's pushing this way, they're going to be repelling each other like that. So how we draw that, if I can just rub those out, rub this out, is we've got in the middle there, all right, we're going to have, is that still eraser? Let's put it back on pen. Whoops, drawing. All right, so circle. We've got one going that way and one going that way because one's a bit bigger. All right, so force number 1, force number 2, and we're going to have a net force. Whoops. So if we took those two away from each other, all right, we looked at them, and they're both, one's bigger than the other, and we took them away. So if we superimpose this one on top of that one, we're going to have a small amount still going that way. All right, so basically what we do is to find the net force, therefore net force, sorry, messy writing, force is going to equal F1 minus F2. All right, if we plug that in, we're going to get an answer of 43.2 newtons to the right. All right, let's work that out. The other one, so question 2, was if Q1 is positive and Q2 is negative. So now force 1 and force 2 are going to be in the same direction, all right, because if they are, if we think about it, we've got Q1 here, Q3 in the middle, and Q2 over here. This guy was positive. Whoop, that's not a very good plus. This guy was positive, all right. This guy here is positive, all right. So from here, this guy's going to be pushing away from this positive over here, all right, because it's going to be repelling. This guy is a negative, so he's going to be attracted, okay, to the center one, because we're talking about if we put ourselves in the position of the third one in the middle, what's going to be happening? So in between here we've got attractive forces, so Q2 is going to move towards it, and if we've got a positive force over here, Q1 is going to move away from it because we're plus in the middle. So what we get there, if we rewrite it, it's a bit messy, sorry, Q3, okay, we've got force 1 is going to be going alright, force 1 this way. Alright, force 2 is going to be going the same way. And then, okay, we get adding them together because they're going the same way. And that's going to be our force net. Okay, so here we add them together because they're going the same way. So force total is going to equal F1 plus F2, and we'll get a grand total of 129.6 newtons, again to the right. All right, and we'll talk more about these directions probably in another example in class to make it a bit clearer. So I hope that that has helped and that you've paused along the way and taken as many notes as you need, and we'll practice some example calculations in class. Alright, see you in the next video.